I'd like to introduce some formulas for logarithmic functions that will be useful. All right? So why don't I write the formulas down first, and then I can derive and discuss. Okay? So the logarithm of the exponential b to the x to the base b, the exponential of the logarithm both to the base b, the logarithm of to the base b of a power a to the k, and a few more. The log to the base b of a product the log to the base b of a quotient Okay, and then finally, one more. Okay, so let me first tell you why these might be useful to you, and then I'll discuss where they came from. Okay, so the first two formulas essentially say that the log and exponential functions for the same base are inverses of each other. Okay, I remember what it means for two functions to be inverses. It means that if you do a composition of both functions, you arrive back at the original, at the x or whatever the independent variable was. Okay, so an exponential of a log of an exponential, both of x, both get you back to x. Okay, the next formula is useful if, let's say, you're taking the log of a power. You can get rid of the exponent. In a sense, you can put it in a simpler place to deal with. You could simply move that k down, right? You could just multiply it by the log of a. Okay, so that might come in handy. Okay, the next one is useful if you have the log of a product. You can break it up into you can relate it to two logs of two smaller numbers. In this case, a and b. In some cases, okay, and then if you have a quotient, you can break that up into pieces, the log of the numerator and denominator, and you subtract them, okay, and then the last formula is useful if you want to express the log to in a certain base with respect to a certain base in terms of a different base, okay. For example, some people's calculator can only do the common base 10 and or the natural base e. Okay, what if you wanted to take the log to the base 7 or 6 or 5 or 100? Okay, this last formula would be useful to express a desired log in terms of maybe the base that your calculator can work with. Okay? So now let's see if we can understand where these come from. Okay, so remember what a logarithm is. Okay, so a logarithm, let's say the logarithm of z to the base b. That's the exponent that b needs to equal z. Okay, you should have that burned in your brain by now. Okay, so now let's look at the first formula again. So we want to know what exponent does b need in order to equal x, in order to equal b to the x? Well, it should be obvious that question mark is equal to x. Okay, so I hope that that makes the first one somewhat more understandable. All right, now the second formula, remember again what the logarithm means. So the log is the exponent that b needs to equal x. Well, if you raise b to that exponent, which is exactly what you're doing on the left side, you're raising b to the exponent that you need to equal x. Well, duh. Well, then of course it's going to equal x. All right? So both of those formulas can be understood if you know the definition of a log that I gave you. All right? Now, for the third one, allow me to do the following. Let me use the second formula to make sense of the third one. Okay? We know that the second formula says that b log b of a is equal to a, right? From the second formula. Okay? Now, let's raise both sides to the k power. Okay? We know that when you have two stacks of exponents, we know that you multiply the exponents together. So, k log of a to the base b. Okay, I just simplified the left side. So, now we have that a to the k is equal to the b raised to k log a base b. Now, take the logarithm of both the last two parts. So, in other words, the logarithm of a to the k power, that's equal to the logarithm of that last blob there. Okay, but once again, now we're gonna use the first formula. The first formula says that the log of this power, this exponential, is equal to the exponent. Okay, so there, I've just derived the third formula. Okay, using the first two, as it turns out. Okay, now for the next one, let me use previously established formulas again. Okay, so let me erase what I've already written in blue so that I have more room. And I'm going to make a statement that's I'm gonna say a times b, capital A times capital B, is equal to a product of exponentials. And I'm going to use the second formula again. All right? So using the second formula, we know that A is equal to B log B A, and B is equal to B log lowercase b B. So AB is equal to B log BA multiplied by B log BB. Okay, now let's do this. Let's first simplify the right side by adding the exponents. Okay, now let's take the log of both sides. And using the first rule, we know that the log of the right side is going to be equal to the exponent. Okay, and there you have it. I've just established the fourth one. Okay, so now we have the third and the fourth. All right, so look that over, make sure that's clear. Let me do something similar now for the fifth one. I already have my formula for a and b in terms of an exponential function, so let me just go ahead and use that. So a divided by b is b to raised to the log b of a divided by b raised to the log b of b. And we know that that's whenever you have a ratio of powers to the same base, we know that we simply subtract the exponents to simplify. Right? Now let's take the log of both sides, the far left and the far right. So the log to the base b of a over b is going to equal the log of the right side. And I'm going to use the very first formula now, that the log of that exponential is just the exponent. So that's going to give me the log of b of a minus the log of b, capital B to base lowercase b. All right, so there you have it. We've established the first 5 formulas. Okay, now for the last one. Okay, and let me go ahead and make some room again, and I'll leave the one formula that I'm going to need to use, a formula involving a and the second pattern. Okay, and this one, it's the purpose of this last one, remember, is if you need to change the base of the log. You need to express one logarithmic function in terms of a different logarithmic function. All right, so here we go. So using that blue formula that I left on the screen, let's take the log to a different base of both sides. So the log to the base c of a, and then on the right side, the log to the base c of b log b raised to the log a to the base b. All right? Now, let's use the third formula to simplify the right side. I'm going to leave the left side the same. The left side is just the log of a to the base c. Okay? And the third formula says we can pull the exponent down. So the log of a to the base b, that's the exponent coming down. And the only thing we have left is the log of lowercase b to the base c. Okay, now let's divide both sides by the log of lowercase b. All right, we have some cancellation on the right side. All right, so what's left over? We have the log of a on the right side left over, and that's equal to the ratio on the left side. Okay, and there you have it. Now I've established all of these log formulas. Please write these down, study them, memorize them, put them under your pillow, and we will be using these a lot. Okay, let me now do some examples to show you how they can be useful. All right, let me go to a new whiteboard. Suppose you had this big, ugly log that you had to take. And let me go ahead just to remind you that if I don't write the base, that it's base 10. So just for fun, let me not write the base. But it doesn't really matter what base we do this in for me to make the point I'm trying to make. But I'm just reminding you that when I don't write it, we can assume it's base 10. Okay, so that's a pretty scary looking log. Okay, Well, let's use the product formula that I just gave you. So can't we write this as the log of 27 plus the log of that cube root? All right. Now, the cube root, isn't the cube root the same as raising something to the 1/3 power? So we can use that power formula that says we can bring the exponent down. So that whole scary looking cube root becomes nothing more than a 1/3 in front of this log. Okay, so far so good. Now we have the log of a quotient, but we have a quotient rule to split that up as well. So the log of 27 plus 1/3 times the log of 729 minus the log of 19,683. Okay, so in the old days, people used to have these logarithmic tables, and they would look up. They had a few calculated for small numbers. Okay, obviously they didn't have every number. So splitting up a complicated log into lots of simple little pieces, you stood a better chance of breaking it up, expressing it in pieces that you had in your log tables. Okay, so that's one reason why you might want to split hairy looking logs into lots of little pieces like I just did. Okay. So another example. All right, let's say that we wanted to know what the logarithm to the base 5 of 100 was. However, our calculator maybe can only do the common base 10. Okay, that's not a problem. We can express this in terms of what our calculator can do. The log of 100 base 10 divided by the log of 5 to the base 10. Okay, and the top one, we don't even have to do that one on our calculator. We know that 10 squared is 100, so that gives 2. So you just need to punch the denominator in your calculator. And if you do that, you'll get 2.861 approximately. Okay? Okay, so let me show you some other examples how these formulas are useful. What if I wanted to solve this equation? 2 to the x is equal to 10. Now, the reason that this one is tricky is because there is no nice exponent that you can raise 2, like 2 to the 3. 2 to the 3 is too small, 2 to the 4 is too big, so it's going to be a more complex answer. Okay? Why don't we take the natural log of both sides? You can take the log with respect to any base, but just for the sake of using the natural log, I'm gonna use that one. Okay, so the natural log of 2 to the x is equal to the natural log of 10. Why do we know that? Because we know that anything you do to one side, if you do it to the other side, the equation will still be satisfied. Okay, so now let's use the rule that's for the logarithm of a power that says you can pull the exponent down. So x ln of 2, x times ln of 2 is equal to the ln of 10. Now we can solve for x. Okay, it's not a simple answer, it's not a pretty answer, but it is an answer. Okay, the log of 10 divided by the log of 2. So that's so these formulas may allow you to solve equations you couldn't solve otherwise. Okay? So you can split up complicated logarithms into lots of pieces. You may want to do the opposite. You might have a bunch of logs added, subtracted, okay, and you want to combine them into a single log for some reason. Okay? You can solve exponential equations. All right, so there's no shortage of problems that you can solve using these formulas.